So we've actually already been talking about spectroscopy, we just haven't been calling it that. And in general, spectroscopy is the study of how light and matter interact. And light and matter can interact in a number of different ways. So matter can both absorb and emit light. And what we've been talking about in geometric optics is matter can also reflect and refract light. But what we're talking about specifically in spectroscopy is particular wavelengths of light that matter will either emit or absorb. And this diagram is a set of collectively what are called Kirchhoff's laws of spectroscopy, not to be confused with Kirchhoff's laws of circuitry. And essentially these are astrophysically relevant. So if you're thinking about a star down here when you see this light source, you're on the right track. And in fact, we'll look at the absorption spectrum from the sun. So this is the type of spectra I've shown you a couple of times with those gas discharge lamps. So these are what are called emission spectra. And basically I can get one of these by putting some hydrogen or some sodium or helium into a lamp, like a little glass tube full of just that particular gas, and then running current through it. So it beats up the electrons, and the electrons, because they can only jump in between particular energy levels, they'll only emit certain wavelengths of light. And each one of these elements, in some sense, because it has a unique spectrum, has a unique fingerprint, and you're able to really do astrophysics because of this. You're able to look at a distant galaxy or star or cloud of gas and determine what's inside of the cloud of gas. So I'll show you a couple of these. This is the type of thing we haven't seen yet. This is a really, and you can find higher resolution pictures of this with more detail, really high res picture of the sun's spectrum. So we use spectrum a little bit casually, but what it technically is if you take all of the light that comes from a source and you basically split it up into its constituent frequencies or wavelengths and tell me how much of each type of light it has. So in the strictest sense, a spectrum would be a mathematical function or graph that tells me how much intensity I have at each wavelength. So here, for instance, it looks like I have equal amounts, roughly speaking, of blue light, green light, yellow light, red light, which is why the sun appears kind of, if you were in space, it would appear a little bit whiter than it is from the surface of Earth. But that's why the sun appears kind of yellow-white in the middle of the spectrum. If the sun was much hotter, it would be whitish or bluish, and if it were much cooler, it would be reddish. So you can determine information about a star or an object, i.e. how hot it is, just based on the overall amount of light coming out. But then there are these particular gaps, and these gaps are the absence of particular wavelengths of light, and each one of those is associated with a certain element. So in fact, the particular wavelengths that are missing from the solar spectrum tells us what's in the cooler cloud of gas at the edge of the solar atmosphere. So particular, I kind of know this one by heart, these really big fat gaps are associated with sodium. So there's sodium in the sun. In fact, this is how we know the sun is actually a recycled star. It's full of all sorts of stuff like iron and calcium. So in general, the mnemonic or cartoon for this is if you just have a hot thing, like a really hot piece of metal or some burning gas, so ionized gas at the end of a cigarette lighter or something like that, that would be what's called a black body spectrum or a continuous spectrum. If that black body or continuous spectrum has to fight its way through a colder cloud of gas, like a hydrogen or helium cloud, the hydrogen or helium will just find its favorite wavelengths of light, in this case, this kind of orangey light, and it'll scatter it away. So what you'll see is an absence of that particular wavelength of light from the light that's made it from the original source through the cloud of gas. And then finally, if I just have the cloud of gas, this is the easiest thing to talk about. We'll talk about it yet again when we get to quantum mechanics. If I just have a cloud of gas, it will emit particular waves of light based on its particular quantum mechanical wave nature. And that's what's called an emission spectrum. So these are those tubes, discharge tubes, where I beat up a gas with electricity, and it only shouts in particular colors. Okay. So let's say we want to do this precisely. This is why I say we've basically been doing spectroscopy. All you really need to do is figure out what those wavelengths of light are. So break apart the whole spectrum. We have two ways of doing that. We can do that with diffractive elements like prisms, so things that bend light different amounts based on their particular wavelengths. So, sorry, dispersive elements like prisms. So because this thing treats different light differently, it'll break it apart, and what the telescope over here will see is a rainbow, essentially. Or we could use a transmission grating in this case. So those gratings, the slight issue with them is that there will be, so for instance, here will be the 0 order peak. Sorry, I'm drawing with a mouse. This is not particularly great. 0th order peak, and then here might be the 1st order peak, m equals 1. And here might be the 2nd order peak, and the 3rd order peak, and the 4th order peak. So you'll actually get multiple measurements are possible with the diffraction grating because you have different orders. But short story is both of these types of spectrometers, they really function in the same way, is they have a way of measuring the angle really precisely, and then they have a telescope, an optical element, which has 2 lenses, one that magnifies and the other one that collects. So this is an example spectroscopy problem. So let's say that I have a sample in a spectroscope, and I'm using a grating. So this grating happens to have 300 lines per millimeter. And we find a red line that's at 10.78 degrees. So just because you might see it, I'll explain the other weird thing in a sec. But for now, we'll just call it 10.78 degrees. So what would this potentially tell me about the sample? So I don't know what this gas is, but I know that it has a line at 10.78 degrees on my spectrometer that's calibrated with or employs a 300 lines per millimeter grating. Okay, so as a little bit of an aside, you might see this. This is degrees and minutes of arc. What the 47 is 47, again, minutes of arc, which is 47/60ths of 1 degree. So that's where the 0.78 comes from. Is that I'm not sure how it started. 60 is just like a lucky number, I guess. Historically, the Sumerians loved it. Is that instead of splitting things, decimalizing the degrees on older instruments, there was a scheme where you broke them up into 60s. So 1 degree is 60 arc minutes, and then 1 arc minute is 60 arc seconds. And by the time you're getting out to arc seconds, you're talking about the width of a finger at a kilometer or something like that. So this works really well. So here's a setup of a prism spectrometer. So here's element that would break up the light into rainbows, and I can't really get the camera down there to see it, so we'll cheat again and use the diffraction grating. So light comes through a collimator, there's a lens there and a little aperture, controllable aperture. So the prism breaks up the light into its constituent colors, and then this arm swivels. So basically you pick a wavelength that you want, so one particular color band, park it there, and then there's such a precise readout or scale on this that it even comes with its own personal magnifying glass that you use. And this gets out to, 1/60th of a degree, actually 1/120th of a degree, because they're half minute of arc markings, so pretty impressive. But we're not going to use that because I can't get the camera down there. So what we're going to do is this old thing again, where I'm just going to show you guys the spectrum and then say, trust me, I took some data and I got 10.78 degrees. So with the diffraction, again, what you would get are different copies. So this is the m equals 0 peak. All light comes straight through. Those would be m equals 1. Because they have different wavelengths, they're going to have different angular locations. There would be m equals 2. You can see they're spread out even more. And then maybe I can get to m equals 3. M equals 3 out there. Okay. And the neat thing about this is every single time you change the element, you change the spectrum, so they all look different. So this is neon. In fact, most of the time when you say, oh, look, it's a neon sign, it's not actually a neon sign. So really quickly, that would be the m equals 2, m equals 1, m equals 0, m equals -1, I guess, and m equals 2. So you can really zoom in. Right. And then this is actually our mystery element that we're going to figure out. And this is the one that I measured that 10.78 degree angle from. So it looks really nice. And then you might be able to see it if I can see through this. So yeah, it's pretty faint, but there is a red line out. You can't go to the front. There is a red line out there. And so 10 degrees off of the center. I don't know if you can see it a little bit better when I zoom in. So I can see it with the eye. I don't know if it's making it up on the CCD, but there is a red line. And that's 10 degrees off of center. So the question is how on earth could I possibly identify this thing based on the presence of that red line if I have that angular measurement? Right. So here's my setup. There's white light coming in. It goes through the collimator. It basically gets split up. So I'll draw a little bit of a schematic of this. Is that there might be, so there's m equals 0. That's just all light coming straight through. That's not particularly interesting. There might be a blue line here. Actually put it here. A blue line here and a red line here. And the reason for that is that because this is a grating, we know that the multiple slit interference pattern that you're seeing, so this is multiple slit interference, is dictated by d sine theta equals m lambda. So for instance, if I have blue light, which might be about, I don't know, we'll call it 400 nanometers, versus red light, which might be 700 nanometers, because the red light has a longer wavelength, then it's going to have a bigger angle. So bigger wavelength, bigger angle, at the same order if those two things are fixed. So this is basically how the prismatic effect works, where this breaks up stuff into its constituent wavelengths, right? But again, we already know how to do spectroscopy. So all I had to do is realize that this 10.78 is the first order diffraction peak. I've got to find out what D is. I've got 300 lines per millimeter, which means 1/300th millimeters in between lines, millimeters per line. So that's 3.33 times 10 to the minus 6 meters for D. And that's really all I need. So I have D sine, we'll call it 3.33 microns. Sine 10.78 equals 1 times lambda, and then math happens. I get lambda equals, 6. Okay. We use meters, 623.4. 6.234 times 10 to the minus 7 meters. And that's just correct, but again, traditionally for visible light, 623.4 times 10 to the minus 9 meters or nanometers, just great nanometers. Okay, so what is it that has that? Well, then I would need a chart. So we'll go back and look at a chart and figure out what's in our mystery lamp. And then with that final answer, so I have 623.4 nanometers, and here are some spectra. In real life, you'd probably have a table. So 600, let's see, that's 650, so that's 610, 620. The only one of these that has something in 624 looks like it's mercury. So it seems like there's mercury in the sample. If you didn't want mercury in your sample, you would have something to say about mercury contamination, for instance, is how this works. And it's just a final note. We pick on visible light a lot, but you don't have to do spectroscopy in just visible light. You can do X-ray spectroscopy. That's how people figure out, for instance, that Chernobyl had a giant accident. They found characteristic X-rays that were associated with the type of radioactive source that Chernobyl used as far away as Sweden and England. Or you could have infrared spectroscopy. So that's really common if you want to figure out how molecules wiggle, so-called Raman shift is infrared So it doesn't have to be visible light. You can do spectroscopy in any branch of the electromagnetic spectrum.